May, June 15, paper 4, variant 2, question 8. A power of a space probe is supplied by the energy released when plutonium decays by emission of alpha. Oh, I didn't know space probe had some radioactive power source. It was space probe, I don't know. It could be a satellite. It could be a Mars rover that just like, the things that get wheels and they go scanning around, beep, 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 and then they collect some kind of things and samples. I don't know, I'm just drawing. So any of these space things can be powered by radioactive stuff. It's a good source. So the alpha particles are emitted in this process of emission. The alpha particles each has some energy, 5.75 MeV, captured and converted into electrical energy with an efficiency of 24%. That's useful. 24% is not great, but I guess it's okay. So you think of it this way. You have some kind of mechanism that will convert the alpha's energy, alpha come in, and come out as electrical energy. So this would be like E equals to VIT or some kind of other electricity stuff. So when you have 5.75 MeV come in, 25% efficiency means whatever comes out and actually can be used is 25%. So the other, don't know how many percent, all lost. I think it's 75%, right? Lost. Loss in heat, loss in whatever other kind of thing. Okay, so this will be useful later when we do some other calculation. So calculate the energy equal to 5.75 eV. This is a conversion from 5.75 to joules. So let's do that conversion right here. Now, gotta remember how to convert EV and joule. 1 EV is equivalent to 5.75 No. What am I saying? No. 1 EV is equivalent to 1.6 times 10 to the negative 19 joules. That's the basic charge. So here, I'm going to do that. So I'll say my energy is going to be 5.75 mega. MeV is mega. So times 10 to the 6 EV. Multiplied by some factor, which is going to be my 1.6 times 10 negative 19 joules per EV. And that will give me a value of about 9.2 times 10 to the negative 13 joules. And that's what I'm going to write down here as well. 9.2 times 10 negative 13. Okay, so final answer, just 1. Conversion lah, make sure you know how to convert, okay? When to divide, when to multiply. Now, the number of alpha particles per second required to generate 19 kilowatts of electrical power. What? Oh, remember we are having a conversion from alpha to electrical energy? There's energy conversion happening here. But there's also power. You can calculate some power here. And that's what they want you to find. If you want a power of 1.9, how many particles do you need here per second coming into this machine? Or this special factory, I guess, in a machine. So if you're not sure how to start off with the definition of power. Power is equals to, oops, my P, E over T. This is like a change in energy, a conversion of electric energy over time. But don't forget, this is many alpha particles being converted. And with a certain efficiency as well. So you gotta be careful. So let's modify our equation a little bit. We are here talking about the power here. So this one has a number of particles, each one of a certain energy E that we calculated just now over a certain time. So we are finding particles per second. Particles per second means we want to find what is N over T. Oh, we have N over T in this equation already. So let's do this. Now, particles required to generate 1.9 kilowatt. 1.9 is our output, right? So this is our power output. Okay. So let's plug in all our values in here. Now there's a problem here. If this is our output power, remember efficiency? Output power is the input power times how many percent? What was the efficiency? 24%. What did I say? 25. 24%. So this is times 0.24. Input power is going to be our NE over T, thanks to the alpha particles. So this will be our final form of the equation. Oh, times 0.24 because of efficiency. Okay, so let's write that here, 0.24. Okay, so this is a backstory lah, why we have to multiply that. Now we can put everything together. So 1.9 times 10 to the 3 kilowatt equals to the input. What is the input? Who gives the input? Alpha particles. How many alpha particles? I don't know. We're trying to find that. So N over T is what we're trying to find. Energy of each alpha is, we just calculated that, is 9.2 times 10 negative 13. Don't forget to also multiply by the efficiency. Okay, so that is on this side. The final value that you get for N over T here should be about 8.605 times 10 to the 15. And this is the unit of particles per second. Particles per second. I'm going to write as 8.6 times 10 to the 15. Particles, usually we don't say as a unit lah. So that's why you see here only got S negative 1 next to me. Okay, so this one is 1 mark here. 1 mark for this whole equation subbing in. Okay, so just remember efficiency, how to deal with that. This thing on the right, no need to write lah if you just put everything in one calculation. Okay, last one. So we know how many particles are coming in per second to generate this amount of power, 1.9 kilowatts. Let's move on to the last part. Each plutonium disintegrates, produce 1 alpha particle. So 1 plutonium, 1 alpha. Plutonium has a half-life of 2.8 years. That's our T half over here. Calculate the decay constant in S negative 1 of plutonium. How to find decay constant? Decay constant is what? Lambda. What equation has lambda and T? Oh, that equation. You can either say it's lambda equals to ln 2 over T half, or your variation that you can find in the data formula sheet is 0.693 over T half. Whichever one you use is fine. So you sub in your T half, let's say over here. That's in years. Oh, but we need seconds. We need to convert years to seconds. How do we do that? I'm going to show you the long unit chain again. In case you're not sure whether to divide or to do what. Years to days. Okay, so years to days. How many days in the year? 365. Okay, so you multiply by 365. Why do we multiply though? Because you want to cancel out the unit of years. So in 1 year, 365 days. That way, year and year cancel out. Okay, convert days to hours. So you want to get rid of days, convert it to hours. So you write the unit like that. Days and days. Cancel out. So in 1 day, 24 hours. Okay, hours to second. Last one. Hours to second. 1 hour got 3600 seconds. Okay, so at the end of the day, if you multiply this, and this, you will get your final unit of seconds. You don't have to write out this whole chain each time. I'm just showing you in case you are not sure. But if you know how to convert straight away without writing out this entire unit step by step, sure, go ahead. So this one will get a value about 7.8 times 10 to the negative 9. Now the mark scheme is pretty flexible here because they know that some people will prefer to use this, some people prefer to use that equation. So you can get about 7.8 or 7.9 is okay. So this one is final mark and substitute in your equation, that's C1. Let's move on to where things start to get real interesting in the next part. If you haven't tried this question, I suggest you try out at least this last part because it's interesting. Anyway, so use your answers to determine the mass of plutonium required for generation of 1.9 kilowatt. What? So okay, back to the machine. You are feeding it some alpha particles. That gives you energy. But in order to create that alpha particle, you're going to need a certain mass. Let's say a lump of plutonium. And then all these will emit alpha. Alpha come out. Alpha come out. So how much? The more mass you have, the more alpha can come out. So what's the mass that you need? Use your answers previously. What was my answers previously? I think it was can't remember. Power? Decay constant? Oh, so we're going to use decay constant, number per second, and energy. to do this calculation. So we're going to put everything together. So how much mass is needed for enough alpha to come out per second to generate that amount of electrical power? Let's do this. How do we start? We are going to start off with the activity equation, because we need to know the number per unit time. This is kind of, N over T, this is activity lah. So if we already found the activity earlier, we can use that as our thing to relate between activity and the number of plutonium atoms. Because if we know the number, we can find the mass. So let's do that first. Activity is dN dt. We already found it earlier. So that is 8.6 times 10 to the 15 per second. That's a lot of particles per second. Decay constant, we just found it. That is 7.85 times 10 to the negative 9. Also in per second. Okay, and we can find the number of nuclei. So this will give me 1.096 times 10 to the 24 nuclei needed in order to generate this amount of power. Okay, so then what next? We need to find mass. So number of nuclei is not enough. They want mass. How are you going to find the mass? Scratch your head a little bit. This is where some conversion between moles is helpful. Now, one thing to know, when you see people write plutonium 236, 236, yes, is a nucleon number to tell you how many nucleons there are, protons and neutrons, but it also tells you another very useful information. It tells you that there are 236 grams per mole of plutonium. So in 1 mole of plutonium, it will be this heavy lah. 1 mole of plutonium. I don't know what amount is that. Put like this little lump in a dish maybe. Well, maybe that's 1 mole. Then it will weigh that heavy, 236. So how are you going to use that to find this thing? We don't know the moles, but we know the number of nuclei, N. So we're going to convert, this is our plan. We need to convert the number of particles to mole, and then from mole to mass. That's the conversion that we need to do here to get the final answer. So let's find the mass. Okay, mass. If you're not sure how to multiply them, hang in there. Hang on for a second. So mass, we're going to start with, let's start with the G mole. So I'm going to write this here, 236 grams per mole. That's for plutonium. We want to find how many grams at the end of the day. And we know the number of nuclei. But that does not really give me any useful information. Okay, never mind. Let's convert mole to particles. So 1 mole defined as the Avogadro constant number of particles. So times 6.02 times 10 to the 23 particles. It's technically not a unit, but let's just write it in. And lastly, how many particles do we have here? We can multiply. So you have 1.096 times 10 to the 24 particles. If you're not sure you're doing this correctly, we check the units. So mole and mole cancel out, particle cancel out. What's left? Grams. Very nice. So you can multiply 236, divide by this, multiply by this. That will give you your final answer of 430 grams. And this one is a final mark, A1. M1, if you convert, do this important conversion from number to mole to mass. And the other one, if you plug into the A equals lambda n equation. So maybe you're wondering, Miss, are there equations we can memorize for this conversion? Yes, there are. The very first one is to know that the mass, how heavy of a sample, that depends on how many moles there are and how heavy it is. This is called the molar mass. I'm going to call this big M. So I'm put a M. Because you multiply mole with G mole negative 1, then you get G ma. Okay, so this is the first equation. The mass of a sample depends on how many moles of it and how heavy is each mole. Makes sense, right? So this is equation number 1. Equation number 2 is the one that relates between a number of particles and all the other things. So this one, in 1 mole, so the number of particles will be number of mole time each mole there are Na number of particles. So these two equations are friends from chemistry that we will use a lot in this chapter. So make sure either you understand how to do the unit method here, or you know these equations. How to relate mass, molar mass, number of particles, and mole. All can be linked together by mole. See the N? Okay, you can create a third equation that equates these two together. Anyway, let's move on to the last part. This one, fuyo! I tell you, the minimum electrical power required for the space probe is 0.84. Okay, so just now we had like 1.9 kilowatt. That's what we can generate, but the minimum we need is this 0.84. Any lower, your space probe is not going to work. So we need to calculate the time in years for which the sample will provide sufficient power. Why? Why does it change? Shouldn't you just put plutonium on the ship and it'll be fine forever? Wait. Plutonium will decay. Energy comes from the decay. So if we draw a graph, a mini little graph of what is happening here, remember that over time, actually I'm going to draw it here. Over time, you have some kind of exponential decay in the activity. Activity, very high, very large power. Over time, low power. So this graph, by the way, can also be converted and adapted to something else. Hang on a second. So let's rewind a little bit. Previously, we talked about where the power comes from. How do we calculate power? Power we did with calculating what was our equation? Ne over T. Or N over T times E. So in this sense, this N over T is activity times E. Of course, there's efficiency as well, but sure. Let's multiply efficiency. What is efficiency? Eta. So the basic idea from this is, you know that power is going to be proportional to the activity. Or you can say power is proportional to the dN dt. So can we create an equation for power? Turns out, yes, we create our own decay equation for power. The power of this space probe will eventually decrease. So I can change this to P. And I can do that because of this proportionality. So if I start off with the initial space probe power of, what was it, 1.9 kilowatts? Over many years, it will decay to some point, which is the minimum, 0.8 kilowatts. And I need that. And I'm wondering, if this is time 0, how long, how many years before it drops to that level and I cannot use it anymore? So we're trying to find the time, how long it takes. So we're going to adapt our exponential decay equation here. So that means we're going to write it again. So P equals to P naught E negative lambda T. It's the same pattern, just different alphabets. So we submit everything now. Okay, so the power now is going to be 0.84 kilowatts. Sure, write it here. It will cancel out lah, but never mind. Let's write it in. 1.9 kilowatts. E negative decay constant. What's the decay constant in years? It's given to us in years. That will be 7.8 times 10 negative 9 and T. Okay, so we got to do our ln and log. So this will be the ln of 0.84 divided by 1.9. The times 10 to the power 3 cancel off already. This side will get negative 7.8 times 10 negative 19 T. Don't forget this decay constant. I use the one in years. There's a few versions. Because if this is in years, my final answer will also be in years for time. So this will give me about roughly... Is it in years? Wait. Let me double check. 7.8. I thought I write in years. What do we find here? Oh! My bad. This one is in second. Per second. Okay, so we'll just switch it up, I guess. This one is going to be in seconds instead of years. Bloop. Per second. So I will get a time in seconds. So my time that I get will be a pretty big number. 1.0464 times 10 to the 6 seconds. I need to convert that to years and I will get about 3.3 years. So this is 2 marks. This is A1 for this mark, the final one. And the other equation mark comes from this one, where you substitute your power values into an exponential decay equation. So over time, your spaceship, maybe at the beginning got a lot of power. Maybe it's a rocket. I don't know. Was this a rocket or a spaceship? Got a window. Maybe very large power, 1.9 kilowatt. But over time, your power will get lesser and lesser. So you got to think of that when you're designing some kind of plutonium powered or radioactive powered vehicles, because your power will change over time if you don't restock it. Okay, so that's all for this question. A interesting one about a space probe and an unusual calculation for power. A lot of people GG'd here when they did this. So that's all for this question. I will see you in the next example or the next section if you're done with this one. Alright, so bye bye.